This presentation is over Chapter 5 of the Zumdahl chemistry book, Gases. End of the Year Project by Tyler Coplen. First, I will begin by giving some information on gases. Gases are one of the three states of matter. Few substances exist in gaseous form under typical conditions, however gases are very important. Gases make up the Earth's atmosphere and the air we breathe every day, consisting of mainly oxygen and hydrogen. This chapter outlines the properties of elemental gases and how they are related. Gases uniformly fill any container. They are easily compressible and mix completely with any other gas. Gases exert pressure on their surroundings. Pressure is measured by the force divided by the area. Barometric pressure is measured by a barometer, an invention by Evangelista Torricelli in 1643. Pressure is often measured in atmospheres, the standard unit for any calculation using pressure. Also, millimeters of mercury, often referred to as torr, in honor of Torricelli, and pascals. At standard pressure, 760 torr is equal to 1 atmosphere, and 101,325 pascals is equal to 1 atmosphere. The first quantitative experiments on gases were performed by an Irish chemist, Robert Boyle, using a J-shaped tube closed at one end, which he reportedly set up in a multi-story entryway of his house. Boyle studied the relationship between the pressure of the trapped gas and its volumes. This relationship is modeled by PV equals K, where P equals pressure, V equals the volume, and K is a constant. Pressure is inversely proportional to volume at a constant temperature. Boyle's law can be used to find new pressures using P1V1 equals P2V2, or P1 over P2 equals V1 over V2. The gases that obey this law are called ideal gases. In the century following Boyle's findings, scientists continued to study the properties of gases. One of these scientists was a French physicist, Jacques Charles, who was the first person to fill a balloon with hydrogen gas and who made the first solo balloon flight. Charles found in 1787 that the volume of gas at constant pressure increases linearly with the temperature of the gas. The volume of a gas increased linearly with the temperature provided that the pressure remains constant. This relationship is modeled by V over T equals B, where V equals volume, T equals temperature, and B is a constant. Volume is directly proportional to temperature when the pressure is held constant. Charles' law can be used to find new volumes or temperatures using V1 over T1 equals V2 over T2, or V1 over V2 equals T1 over T2. Temperatures must be measured in degrees Kelvin. In 1811, the Italian chemist Avogadro postulated that equal volumes of gases at the same temperature and pressure contain the same number of particles. This observation is called Avogadro's law. Stated mathematically, Avogadro's law is V over N equals A, or V equals AN, where V equals volume, N is the number of moles, and A is a constant. Volume is directly proportional to the number of moles when temperature and pressure are held constant. For a gas at constant temperature and pressure, the volume is directly proportional to the number of moles. Volume and the number of moles can be found by using V over N equals V over N. The ideal gas law is an equation of state for a gas, where the state of the gas is its condition at a given time. A particular state of a gas is described by its pressure, volume, temperature, and number of moles. Knowledge of any three of these properties is enough to completely define the state of the gas. Since the fourth property can then be determined from the equation for the ideal gas law, it is important to recognize that the ideal gas law is an empirical equation. It is based on experimental measurements of the properties of gases. A gas that obeys this equation is said to be behave ideally. The ideal gas law gives the state of a gas under given circumstances. It is modeled by V equals KBA Tn over P, where K, B, and A are constants of Boyle's, Charles, and Avogadro's laws. K, B, and A combine to create a universal gas constant R, which is 0.0821. Missing values of pressure, volume, temperature, and number of moles can then be found using PV equals nRT, where P equals pressure, V equals volume, N equals the number of moles, R is the universal gas constant, and T equals temperature. The ideal gas law works well at low pressures and high temperatures. Most gases do not behave ideally above 1 atmosphere pressure. The ideal gas law does not work well near the condensation conditions of a gas. The conditions 0 degrees Celsius and 1 atmosphere, called standard temperature and pressure, abbreviated STP, are common reference conditions for the properties of gases. For example, the molar volume of an ideal gas is 22.4 liters at STP. Many chemical reactions involve gases. By assuming ideal behavior for these gases, we can carry out stoichiometric calculations if the pressure, volume, and temperature of the gases are known. Among the experiments that led John Dalton to propose the atomic theory were his studies of mixtures of gases. In 1803, Dalton summarized his observations as the law of partial pressures, which states, for a mixture of gases in a container, the total pressure exerted is the sum of the pressures each gas would exert if it were alone. The total pressure is modeled by the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 plus the pressure of any other gases involved in the formula. The subscripts refer to the individual gases. If the gases act ideally, each pressure and the total pressures can then be determined by calculating the ideal gas law. The kinetic molecular theory, or KMT, is a simple model that attempts to explain the properties of an ideal gas. This model is based on speculations about the behavior of an ideal gas particles. The postulates of the kinetic molecular theory as they relate to the particles of an ideal gas can be stated as follows. The particles are so small compared with the distances between them that the volume of the individual particles can be assumed to be negligible, or zero. The particles are in constant motion. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. The particles are assumed to exert no forces on each other. They are assumed neither to attract nor to repel each other. The average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. To explain the observed behavior with KMT, you must first look at the relationships between certain elements of the ideal gas law. The first of these relationships is pressure and volume. As V is decreased, P increases. Volume decrease causes a decrease in surface area. Since P equals the force over the area, the decrease in V causes the area to decrease, increasing the P. The next relationship is between pressure and temperature, where V is held constant. As T increases, P increases. The increase in T causes an increase in average kinetic energy. Molecules moving faster collide with the walls of the container more frequently and with greater force. The third relationship is between volume and temperature when P is held constant. As T increases, V also increases. Increased T creates more frequent, more forceful collisions. V must increase proportionally to increase the surface area and maintain P. The next relationship is volume and the number of moles, where temperature and pressure are held constant. As the number of moles increases, volume must increase. Increasing the number of particles increases the number of collisions. This can be balanced by an increase in V to maintain constant P. The final relationship is Dalton's law of partial pressures. P is independent of the type of gas molecule. KMT states that particles are independent and V is assumed to be zero. The identity of the molecules is therefore unimportant. We have seen that postulates of kinetic molecular theory, when combined with the appropriate physical principles, produce an equation that successfully fits the experimentally observed behavior of the gases as they approach ideal behavior. Two phenomena involving gases provide further tests of this model. The first of which is effusion, which is the movement of a gas through a small opening into a vacuated container or vacuum. Thomas Graham, a Scottish chemist, found experimentally that the rate of effusion of a gas is inversely proportional to the square root of its mass of its particles. Stated in another way, the relative rates of effusion of the two gases at the same temperature and pressure are given by the inverse ratio of the square roots of the masses of the gas particles, given by the rate of effusion for gas 1 over the rate of effusion for gas 2 equals the mass of gas 2 square root over the square root of mass 1. The second phenomena is diffusion. Diffusion is the mixing of gases. It is a quantitative analysis of diffusion requires a more complex analysis. Diffusion is complicated to describe theoretically and mathematically. Thank you for watching. I hope this slideshow has been a good source of information over Chapter 5 of the Zumdahl chemistry book, Gases.